Yo, what's up? I'm James, and today I'm going to show you guys how to solve this premium LeetCode hard problem called Alien Dictionary. So this problem I really like because it forces us to use a couple different data structures um, to solve this problem. And it's a pretty interesting problem. So if you see, we are given a list of strings. We're given an array of strings um, that are supposedly from an alien languages dictionary. And the strings are sorted lexicographically, so like a dictionary is, by the rules of this language, right? So in this language, C could come before A, blah, 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 so on. This is not our dictionary. It's a completely new dictionary, and all we know about the rules of this dictionary is the order that these strings are given to us in. All right, so what we are learning from our input here is in our real dictionary, right? Apple and apricot, the apricot would come after apple, and the only thing that this tells us is that R comes after P, right? Because these are the same, and then we look at the first differing letter to know um, what order these words would go in lexicographically. So in this example, we have WRT and then WRF, and right, this is just telling us T comes before F. That's all this tells us. We don't know anything about W, right? Nothing's coming before this. Like, we don't know, and whatever. W could be the first letter in the alphabet, right? And then similarly, like we look at ER, this is telling us, since it's coming after these words, that E comes after W, right? That's all. It doesn't tell us anything else about R or anything until we see the next word, right? Well, now we know T comes after R, right? Right. Given our input string or input array of strings, we can kind of decipher what the dictionary looks like, right? Based on all these little relationships. And really what we need is a way to represent this. First, let's figure out what are we being asked for, right? So if if we cannot, right, if the given arrangement of string in words cannot correspond to any order of letters, return blank, right? So if we were given some sort of dictionary that wouldn't be possible to, okay, actually, this is a bad example. If we were given like ER, ETT, and then like ERW, right? This isn't possible because this is telling us T comes before R comes before T, and then this would be T comes before R again, right? Impossible. So if it's impossible, return nothing. If it's possible, return a string of the unique letters in the new alien dictionary sorted lexicographically, right? So return a string of the unique letters. So this is saying we have to return all the unique letters in a string, sorted lexicographically according to these rules that were given from the initial input. So if we think about our dictionary, right, or our alphabet, we have like A, B, C, and D. So we can like define our alphabet like, all right, well, A comes before all of these, right? So it's a one-way edge between A and B. And then B comes before C and D. And then C comes before D. Okay, so here we have this graph describing the relationship of letters. the order of letters, right? The lexicographical sorting. So, and then like, let's say we're trying to do what the question is asking. We're trying to output the string of unique letters in order. So we know the answer to this, right, is A, B, C, D. That's what we'd be looking for. We want that equivalent in what we're given, right? So how would we do this? Well, we'd start from the first letter, which is the letter with no edges coming in. And then we look at all the ways we can go out. And how do we know B's next? Well, we look at these other neighbors and like C, well, C has another edge besides just the edge we're looking at, which is from A to C. It has another one. So we know, well, another letter is going to come before C. It's not just A. So we don't put C next. And similarly with D, we don't put D next. But looking at B, we can see that this is the only edge going to be. Once we have A, now we can place B because there's nothing else coming before it, right? So we go A, B, and then we look at B's. Where does B can go to C and D? Well, like we already used A, so we can actually cross out these edges. We used A. We use B now, so we could cross out like this edge and this edge from B to C, and it's kind of hard to see now, but now there's no edges going to C, so C's next. D still has an edge, so we know like because there's an edge, we know there's a letter that is going to come before. That's what the edge represents, is a letter coming before in the lexicographical sorting. So that's how we can arrive from our graph to the output that we want, right? So now we just need to apply this in code to our problem. So we need to create the relationship, we need to create the graph, and then we need to traverse the graph similarly to how I did, just drawing it, and we should be able to get our answer. So how do we store these like relationships? Well, you saw like when we were looking at each letter, we had to look at every single option we could go out to. So what we can do here is we can create an adjacency list, which is a map. Okay, so it's a map of, given a node, the value, given the node is going to serve as the key in the map, the value would be a list of all the connecting nodes. And then we have an integree. We also have an integree map. And same thing here. The reason we need the integree map is because we need to know how many edges we have going into a node, right? Because that will tell us, like, we knew A could come first because there was no integree. There was no edges pointing in to A. So this is something we need to keep track of, and we don't need the specific nodes coming in. We just need to know how many. That's all we were looking at, right? When we were building A, B, C, D, we were only looking at how many edges we have left coming in. It didn't matter what they were. Now we need to populate, right? We need to fill out the data. So we can go through each word of words. We don't need our specific index here. And we can say, actually, maybe we do need the index. Yeah, we do want the index. So because we actually want to compare every word to its next word, right? So we can do -1, less than -1, because we don't need to go to the last element. We just need to go to the one before it and then compare them. Basically, we say word 1 is equal to words I, And then word 2 is equal to words I plus 1. Okay, and then we're gonna loop through, and we're gonna find the first different character, because that's what is that's the information we care about. It could be the first one, right? But we have to figure that out like systematically. So we know that our length is gonna be the min of these two, the minimum length of these two. And actually, before we do this, we have to initialize our map for each character, right? So let's do that real quick. So it's let char of word. So we're going through each character of each word in our list, and we just need to initialize our data structures here. So we can go list set char, and our adjacency list is a set of elements, and our in degree is 0. So we're just going to initialize our data set, our data structures here. Back to this. So now we know we know what our bounds are for this loop, right? It's less than the length that we just calculated. And we're going to say if word 1 j, so if this character does not equal the character in the other word, now we know that there's a relationship here. And we know in our adjacency list that word 1 j comes, or here, I'm going to get, so this character in the first word comes before the next one, right? So we get our adjacency list, and then that's a set, and we're going to add to the set this character in word 2, okay? And for our in degree, here's where for word 2, we need to we know that there's now an edge going in, so we set it to what it currently is plus 1, right? We need to increment. So we're 2j plus 1, and we know it's initialized to at least 0, so we can directly add 1 here. Oh, we also have to say here, so if this relationship has already been found, right, we don't need to like record it again. So like if we already know f comes after t, and then like in some input could give us this relationship twice, so we don't need to record it twice, because then we'd be adding the in degree too many times. So we have to say like if word 1 j dot if this set has word, if this already has word 2j, or if it doesn't, then we record, right? So this condition is crucial, and then we know once we've found the first difference, we can just simply break. We don't need to like keep comparing characters within here. All right, so this creates our relationship mapping, and now all that's left to do is traverse our graph. We can do a depth first or breadth first search here. I think a depth first is just going to get us our result like slightly quicker, because we're not concerned about comparing all the different answers there might be. We just want to return the first valid one. So with our traversal, we need a while loop, and we are going to use a stack. And yeah, we say, so the first element that we're going to start from, we're going to go through our in-degree map and take the ones that have no in-degrees and start with them. So add those to the stack first. So we can say like of in-degree. So this is just taking our key and our value of our map and iterating through. And we just say if degree is equal to 0, push this character to the stack. Okay. And now we say, well, there's a stack. So this is just typical depth first search here. We can say char. Yeah, we literally just are using the char. Like that. And then we can say for all of our neighbors, and we get our adjacency list of this character. So this is a set that we're retrieving. And for each neighbor, we need to, so similarly in how we were figuring out the A, B, C, D order, we were, for our element, for all the edges going out of our current element, our current node, we were looking at the first element that like only had this element before it. So for B, it was B, like from going from A to the next letter, it was B, right? B was the only element that just had A before it. So the way we can like represent this in code is we take our in-degree list and we decrement it for the like representing the current node that comes before. So we set it to -1, and then we say if this is equal to 0. So if it's 0, now we can add it to the stack. Now we know it can come next. So we say stack push or we push the neighbor here. This is for the neighbor. Okay. So if it's 0, we push it on, and then we move on. Okay, so the last thing we need to do is we need a result to return. So our result's also an array. And we're just going to append the result every time we pop something from the stack. So we can push the character there. All right, so once we've traversed everything, we've hit all the neighbors. Now we can just return result, a result joined. So that's how we join the array. And there is one last step here. I'm going to run this. All right, so we're passing our base cases. Cool. And now let's see where we fail here. So, okay, here we outputted something, but we want to output nothing, right? Because this is an invalid dictionary. We have a prefix coming after the word that it's a prefix of, right? So in a real dictionary, the word with fewer letters, like if every letter matches up to a certain point, the word with the more letters comes after. That's just how a dictionary works, and lexicographical sorting, how that works. So this is invalid. We shouldn't be returning anything. So there's an edge case here we need to check for, and that is if word 2, or if word 1 starts with word 2, and word 2.length is less than word 1.length, we return nothing. Okay, so this is an edge case that we're accounting for. All right, now here we're failing this case, and that is because, and this is a cyclical graph. Okay, so we say x comes after z, a comes after x, and then z comes after a, right? That's a cyclical graph. This is an invalid dictionary. Like z can't come after a and before a at the same time, and we're still returning something. So essentially, since there's a cycle, we didn't hit every, or we didn't decrement every in degree value to 0, right? That's how we would know that we used every unique letter in our alphabet, is if our in degree becomes 0 for all of our every in degree key in our map, right? So basically we have to say if our result length is equal to our in degree map size, so this is how many keys are in in degree, right? So if it's equal, then we return our result. Otherwise, we would just return nothing. Okay, so this is just our quick way to say like if we've used every unique character, because if we haven't, then we know there's a cycle, there's a part of our graph that we can't get to. So now we run this, and there we go. Okay, so and it's pretty good complexity, 1 millisecond. I guess that's pretty fast. So cool. Hopefully that felt pretty straightforward. All we did here was we used 2 maps to store an adjacency list and an in degree list, and we created our graph with these 2 mappings, and we just went through our list of words and created these relationships according to how we know the rules of a dictionary operate. And then we iteratively did a depth first search on our graph and returned the result. So yeah, feel free to leave any questions you have in the comments, and I'll see you in the next problem.